So, dear students, let us start with the fine structure. The very first question arises in our mind is what's fine structure? I mean, talking about Bohr model of hydrogen atom or hydrogen-like atoms, what we have is we have line spectra. And when we closely look at the line spectra of hydrogen atom, what we see is what we observe is this line is basically made of uh, more lines, and these lines are closely packed. So, so this feature of observation that we have for hydrogen atom, this fine structure can be explained using the quantum mechanical treatment. And what we have ordinarily, if I start uh, with a Hamiltonian operator, uh, if it operates on a wave function psi ml ml, what we will have is we will have the eigenvalues en, and we will have the original wave function. And this 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 H cap is a Hamiltonian operator, and and the energy that's evaluated from this equation for hydrogen atom, it comes out to be En is minus RHc by n square z square. So the equation there we have for hydrogen or hydrogen-like atoms, uh, and this Z is the atomic number, or it's the Rydberg constant, and H is the Planck's constant, C is the speed of light, and N is the principal quantum number. And the symbols that we have here, this N is it refers to the principal quantum number, L is the orbital quantum number, and ML is the magnetic quantum number. Now, what is so obvious about this equation is that this equation uh, is a result of treating a hydrogen atom as an ideal system, an unperturbed system, where we have an electron, and this electron is revolving around the nucleus. A nucleus whose mass is assumed to be infinite with respect to the mass of an electron. And to move on from here, what we have is if I calculate the expectation value of this Hamiltonian operator, we can say it that way as well. If I calculate its expectation value, so that's going to be sine NL ML H sine psi NL ML, sorry. And and what we will have is we will have En and psi NL ML psi NL ML, and we have the normalization, assuming this function psi NL ML to be normalized, and this the result that we will obtain by calculating the expectation value of the Hamiltonian is going to give us it's going to give us En, and En is the energy, and this energy is dependent on the principal quantum number. And what we have is we have different states of this hydrogen atom. We have ground state, and this atom can be in excited state as well. That can be defined in terms of this principal quantum number n, because this n can take the values 1, 2 as integral numbers. So, so what is so important here is that this is not the reality of hydrogen atom. This is not. It's not like that this hydrogen atom has. It has only the involvement of the kinetic energy and the potential energy between the nucleus and the electron. What we have assumed here is we have assumed that the nucleus has infinite mass, and electron is revolving around the nucleus, and there is electrostatic interaction between the nucleus and electron, and probably the energy that this electron has is kinetic energy, but no relativistic effects are imposed in this kinetic energy. So what we have is we have H, I'll represent this as H naught, as the ideal Hamiltonian for hydrogen atom. So suppose if I take an example of, say, for example, we have a pendulum, and if this pendulum oscillates, the oscillations uh, under gravity, they'll go on forever. But because there is presence of air, resistive forces, and these resistive forces always influence the oscillations of this pendulum, and the amplitude of this pendulum goes on decreasing slowly. So I can say that the interaction of the resistive forces with the system, this interaction is what's called as perturbation. So the point here is that the involvement of the perturbation, the magnitude of an perturbation is always small in nature. So so uh, so to go with the problem of hydrogen atom or hydrogen-like atoms, would like to define the overall Hamiltonian as H dash, and this H dash consists H naught, it consists HRK, it consists HSO, and it consists H Darwin. So this is the original Hamiltonian, and this is the Hamiltonian due to the relativistic correction in the kinetic energy, because what is happening in an atom is that electron is moving very fast, uh, and uh, and the speed of this electron is quite close to the speed of light. So certainly there has to have the incorporation of relativistic kinetic uh, energy to the original or ideal Hamiltonian. And then there is another term that is HSO. This HSO is the correction to the original Hamiltonian due to the spin orbit interaction. What we have, if I take a hydrogen atom, we have nucleus and we have electron, and the electron is revolving around the nucleus. And since the electron is revolving around the nucleus, it has a charge, and whenever we have acceleration of the charge, because it's going to move in with some with the change in its velocity at every point, and this change in velocity at every point leads to acceleration, and when charge accelerates, what it does, it uh, it is equivalent to it emits electromagnetic radiations, and it is equivalent to a current loop that we have here. And when we have current loop, we understand that magnetic field is associated with it. So the electron has magnetic field associated with it, so it has magnetic moment, and at the same time this electron is spinning uh, on its own axis. We cannot give the physical interpretation of this electron when it comes to quantum mechanics. But for the sake of understanding, we are choosing the classical lines. Otherwise, the classical lines have nothing to do with the procedures and outcomes of the quantum mechanics. So we have here spin associated with the electron, and this spinning electron also has magnetic field associated with it, and certainly there is an interaction between the spin magnetic moment of electron and the orbital magnetic moment of electron, and there is we can have the Hamiltonian for this spin orbit interaction, and on calculating the expectation value of the spin orbit interaction, we will have the correction in energy to the original energy, to the energy that's ideally calculated for hydrogen or hydrogen-like atoms. So, so to move on from here, then we have the Darwin term, and this Darwin term is based on the concept that the electrons in the orbitals L equal to zero. So L equal to zero is the s orbital. In these orbitals, the speed of electron is more than that of the speed of the electrons in other orbitals, and this gives birth to some kind of quantum fluctuations, and these quantum fluctuations uh, they come up in the form of energy, and we have the further correction in the original Hamiltonian of hydrogen or hydrogen-like atoms, and on calculating its expectation value, we can have the magnitude of energy that needs to be added to the system in order to have the correction to the original energy. So here we will start our discussion with HRK. So what is HRK? It's assuming that this HRK represents a Hamiltonian as a correction to the original Hamiltonian, as I should call it, a relativistic correction in kinetic energy. So moving on from here, let's start with this correction. What I have is we are in the domain of relativity now. The electron has relativistic effects, and we have this total relativistic energy of an electron can be written as E equals p square c square plus m naught square c to the power of 4 whole raised power 1 by 2. Let us start from here, and we can write down. So we have the symbols have their usual meanings. P refers to the momentum, C is the speed of light, M naught is the rest mass of this electron, and E is the relativistic energy. Now, if I have to write down the kinetic energy, the relativistic kinetic energy, that's going to be E minus the rest mass energy. This is the case. Okay, so I can find this k. For E, I'll be using this equation, that is p square c square plus m naught square c to the power of 4 whole raised power 1 by 2 minus m naught c square. So that's it. So we can have further simplification. I think we can get m naught c square common from this equation, and when I do that, what I'll have 1 plus p square c square by m naught c square whole raised power 1 by 2 minus m naught c square. Now, if we'll take it back into the brackets, we'll get the same thing. So this is going to give me m naught square c to the power of 4, and when it will go inside, it's going to become it's going to become m naught c to the power of 4. Right. So this is minus m naught c square. So that's correct. Now let's move on from here. We can immediately think about using binomial expansion for this bracketed term. So what we will have, and we understand, if we have something like 1 plus x whole raised power n, we can write down it as 1 plus nx plus n into n minus 1 by 2 factorial x squared plus so on and so forth. So what we will do here is that we will use this binomial expansion for this bracketed term, and we will be neglecting the terms above this term. So all we will do is, because their contribution is small, and we can neglect them, and we can use first 3 terms of this binomial expansion. So when we do that, what we will have is we will have k equal to m naught c square times 1 plus n, so it is 1 by 2. Yeah, it is p square c square by m naught c square. Okay, this is the first term. Then what I have is n times n minus 1 by 2, so n is 1 by 2 times 1 by 2 minus 1, that's minus 1 by 2, so this is minus 1 by 8. So this is minus 1 by 8 p square c square by m naught c square whole square. So we have neglected the higher order terms, so finally I'll have minus 1 here, and I'll close the bracket. So we can immediately see that this 1 and -1 will cancel. So what we will have is kinetic energy is this m naught c square. I'll take it inside the bracket. What I'll have is 1 by 2 p square c square by, if it goes inside, it has to be m naught square c to the power of 4. I have to correct it there. Yeah, because when it will go inside, it will be m naught square c to the power of 4. So they have to cancel so that we get p square c square. So this is m naught square c to the power of 4. That should be the correct thing. And this should be corrected here. Also, this is m naught square c to the power of 4. Okay, so when this m naught c square will go inside, what we'll get is we will get for m naught, I'll get m naught only, and c square will cancel, and c square and c square will cancel. So finally, I'll have this term, and then -1 by 8. Then what I'll have, m naught c square will go inside. So 1 m naught. So this is basically p to the power of 4 c to the power of 4 divided by m naught 4 and c to the power of 8. Okay, so when we take this, I would like to write down it as a step over here. So now this k comes out to be, here I will have c square and c square. The c square and c square will cancel, and here what I'll have is raised power 4 will cancel, so I'll have cube over here. Then this 8 will go with 4, so you'll have 4 here, and this 2 will go with this 4, and you will have 2 here. So what we have is p square by 2m naught minus 1 by 8 p to the power of 4 by m naught cube, and probably 4 and 4 has cut, so it is c square. Now, this is the original kinetic energy, and this -1 by 8 p to the power of 4 by m naught cubed c square. This is the term. This is the correction in terms of the relativistic kinetic energy. And to calculate this, so what is it? I can write down this HRK. This HRK is -1 by 8 p to the power of 4 by m naught cube c square. And we can use the operator for formulation here for this Hamiltonian. So what we will have is we will have the correction in terms of energy, that is ERK. And this correction will be the result of calculating the expectation of HRK, and that's going to be psi NL ML, then HRK psi NL ML. All right, so we can use here, we will have psi NL ML and minus p to the power of 4 by m naught cube c square psi NL ML. And let's get these constants out. So what we'll have is it is -1 by 8 m naught cubed c square psi NL ML p to the power of 4 psi NL ML. So let us keep this whole thing as say I'll use this thing as beta, and what I can do here is when we deal with bracket, what we have is that the scalar products are equally valid in as inner products in this bracket, and what we can write is psi NL ML p raised power 2 dot p raised power 2 psi NL ML, and I can write it beta p raised power 2 psi NL ML p raised power 2 psi NL ml. Now we can use for this p square, we can use the expression for p square. What we have basically is we can write that this p square, this p square by 2m, which is kinetic energy, plus potential energy, gives us the total energy. So for p square by 2m is going to be E minus V, and this implies this p square is E minus V times 2m. So what we can do is we can replace p square by the same expressions. So this is beta. For p square, what I have is E minus V. So 2m, I can get that out. Psi NL ML, and E minus V psi NL ML. So we can have the inner product of this bracket. So what we'll have is 2m beta is. So we will have E psi NL M L psi NL ML. Okay, this is the first thing. The second thing will be minus E, then the expectation of V, and psi N L M L psi N L M L. Then we will have the same term minus E V psi N L M L psi N L M L. Okay, finally what we'll have is plus expectation of V square psi NL ML psi NL ML. All right, and what will be the result of this? This is going to give me En, and this is this is going to give me En, because psi NL ML, psi NL ML, they are both assumed to be the normalizing wave functions. So from here we will have En, and from here we will have one for this, one for this, and one for this. So what will be the result that we will obtain here is this E or K will be 2m beta. Then what we will have is we will have En, then we will have minus twice En expectation of V, then we will have plus En, no, there is no En, plus expectation of V square. Okay, that should be the case. Yeah, that should be the case. So so what we have is we have to have the expectation of potential energy, and the square of potential energy. And what we do for that is we have the expression for the potential energy as minus ZE square by 4 pi epsilon naught. So here what we will have is the expectation of 1 by r. And similarly for V square, what we will have minus ZE square by 4 pi epsilon naught whole square. Then we will have the expectation of 1 by r square. So on calculating the expectation value of V and V square, finally we come up with the correction in the form of relativistic correction in kinetic energy. And the final expression that we obtain is ERK is minus RHC by N cube alpha square Z to the power of 4, and then 1 by L into L plus 1 minus 3 by 4n. And this alpha is called fine structure constant. Fine structure constant. And the value of this alpha is E squared by twice epsilon naught Hc. Now we can see that we have this relativistic correction in kinetic energy. It's showing the dependence on the orbital quantum number. Now, in addition of showing its dependence on the orbital quantum number, we can see that this ERK is negative. It depends on the fourth power of the atomic number, and it is inversely proportional to the cube of principal quantum number. and and to look for to look for its dependence, to look for the dependence of this relativistic kinetic energy. Now, if I take the n is equal to 2 state for hydrogen atom, or hydrogen-like atoms. Let's choose the hydrogen atom. For n equal to 2, L is going to have two values, that is 0 and 1. So what is happening here is you have n equal to 2, and for this I have L1 and I have L0. So L is 0 and L is 1. So what is important here is that we can see that the result that we have obtained here for relativistic correction in kinetic energy, it has the dependence on this orbital quantum number, and for the given n, you have two values of orbital quantum numbers. So there is splitting, and this splitting is due to relativistic kinetic energy. And for L equal to 0, we call it S state, and for L equal to 1, we call it P state. And the similar analysis can be done for another state, say for n is equal to 3 state. We can have the further splitting of the line spectra. So relativistic correction in kinetic energy of the electron, it gives a sense of understanding that why there is the splitting of the line spectra. When the line spectra is closely examined, it's found to be made of many lines, and this splitting can be understood in terms of relativistic kinetic energy. And further, we can when we'll on discussing the spin orbiter interaction, because that will also come in the form of correction to the original Hamiltonian for hydrogen atom or hydrogen-like atoms.